in Germany, and I'm going to talk about the need and opportunity for improved modelling of land use decision making. Or perhaps not. Okay. I think at a really general level, the need for modelling of this kind is perhaps best illustrated by these two plots. On the left, showing modelled pathways towards roughly net zero CO2 emissions by mid-century in order to limit global warming to 1.5 degrees Celsius. And on the right-hand side, these model projections of the ongoing loss of biodiversity around the world. Both of these major challenges depend fundamentally on landscape processes, and so the models that we're using to develop these pathways to address these challenges fundamentally must represent those landscape processes in some way. And we have a parallel for doing something like this in global climate models, although after Simon and Justin's talks, perhaps hydrological models would have made a more relevant parallel. But climate models have, over the past few decades, identified crucial processes, modeled them in isolation, gradually increased the level of detail with which they represent those processes, and integrated them together into the very large-scale, increasingly high-resolution climate models that we have today, and which are very widely used, of course, across scientific fields. And we can, in parallel, identify crucial or key landscape processes. For example, this is one of many potential identifications of key processes in land use decision making, the processes that happen when people decide what to do with land. In this case, there are 6 key processes: learning, experiencing, communicating, deliberating, competing, and finally acting before going back through the cycle. And in parallel, key processes, biological processes, landscape ecological processes have been identified. In this case, for predicting biological responses to climate change, and this paper suggested that evolution, species interactions, dispersal, demography, physiology, and environmental change, or land use change in particular, are the key processes that need to be considered when modelling those responses to climate change. So these give us a potentially debatable, but at least some idea of the basic coverage that these models should have. And in reality, we're modelling quite different things. You can see the red line here. This is a plot of the number of studies predicting extinction risks from climate change over the past few years. And the total number of studies has been skyrocketing, as that red line shows. But the lower lines reach just under 1/4 of those models are including even one of these key processes. So most of those models aren't including any key biological processes when predicting biological outcomes. And none of them are including all 6 of these key biological processes. So there's a major gap evident there. And in parallel, it's a slightly different plot, but it shows basically the same thing for social systems. We are modelling something like 80% of models are including one key behavioral process, but that's almost always economic rationality, optimization. Very few models are including 2 processes. None are including even 4 behavioral processes when simulating land use responses to climate change. So again, we're simulating outcomes without simulating the processes by which we know those outcomes develop. And the results, I would argue, are partially visible in this plot that I showed already. The gold lines here are policy interventions that seek to alter the trend of biodiversity loss around the world, with the statements given above them. And you can see, although it's a schematic, you can see that they've had little or no effect on the very thing that they're attempting to alter, partly because they're not based on the knowledge we have about how those systems operate. So there's a clear need for better models, I think, of landscape processes of this kind. But as I said in my title, I think there's also an opportunity, and this has been covered by previous speakers much better than I will cover it, but I wanted again to draw the parallel between ecological sciences and social sciences, which of course go together at the landscape scale. In ecology, we have very long-term and widespread data bases, like this one provided by the Forest Geo Network, that includes repeated complete spatial censuses of forest plots all around the world that are used very widely in forest ecology to study ecological processes. And we have similar initiatives developing in social science. For example, the Global Collaboration Engine that provides access to social survey results, social scientific case studies all around the world, which can be used to develop more general understanding of social landscape processes. And of course, as other speakers have said, we have increasing numbers of increasingly high resolution remote sensing data that can begin to give us an idea of how ecosystem state and even function is changing over time, and to some extent how the state of social systems, land use systems, is changing as well. So we have this sort of data explosion, big data becoming available, and to some extent, well, to a large extent, we're not yet capitalizing on that, but we do have approaches that can do so. Others have mentioned machine learning. This is increasingly being applied to look at the supply and demand for different ecosystem services, including very awkward services, cultural ecosystem services. In the bottom paper is an example of using crowdsourced images from uploading sites like Flickr to look at the cultural services people tend to take photographs of and tend to share online, and therefore to develop some kind of understanding of which services are important to people in which places. Those data can also be used to develop new generalizations or aggregations of data to provide more informative models. This paper suggested the use of human or agent functional types in analogy to the use of plant functional types in vegetation models, which are used to boil down, to reduce complexity and isolate the key differences between groups of species in order that they can be efficiently simulated over very large spatial scales. And this paper suggested that you can do a parallel process with land users, identifying the capital space, the environmental conditions that they need, that they exploit to produce things, and the services that they provide, and therefore their competition on the land surface through time. And this parallel or analogy has recently been extended in this paper on the right, that showed that just like in ecological communities, as you increase the richness, the functional richness of social actors, of land users, you increase system resilience and also the provision of ecosystem services in socio-ecological systems. So this reduction of real-world complexity to the level of functional types, somehow focusing on the main roles of the different actors in these systems, appears to capture quite a lot about the dynamics and how the systems themselves develop through time. We also have a lot of models we can use. This table is just here as an example. I'm sure you've all seen many similar tables in review papers listing lots and lots of models. This paper reviewed European agricultural agent-based models. Last year it found 20 of them. I'm not sure it was meant to be systematic. And they all covered different factors and processes with different levels of detail. So although there's an awful lot we're not modeling, we have the technical capacity to do that, to capitalize the data that we're gathering, use these new analysis techniques, and to put this knowledge into models that already exist, or that we build again using the knowledge we have about modeling. So in the second part, I wanted to give some example results of what happens when we go through this process of identifying key landscape processes, putting them into process-based, agent-based models, and seeing how the results differ at the end. And these results that I will show come from just one possible model. It's the one that we've developed and used. It's called the Crafty Agent-Based Modeling Framework. It's been applied in Europe to the European scale, to Scotland and to Sweden, with different levels of spatial resolution and different levels of land use and ecosystem resolution. And I just wanted to show the effect of including non-economic motivations in this model, allowing modeled actors to make decisions on the basis of financial factors plus environmental or social factors, allowing the model to operate in disequilibrium, so not enforcing any particular dynamics on the model, allowing institutional behavior to exist in the model as a dynamic process, and including socio-ecological feedbacks. In the first case, when we include non-economic motivations, we find that we quickly go from the top plot of a very stable and quite homogeneous land use pattern to the bottom plot, which you may be able to see is more fragmented and patchy. And the box plot there just shows this increase. As we include supra-economic motivations, we find this sudden spread and higher level of fragmentation. We also find a slower response to purely economic drivers, which may be expected. If we include social networks as a way of disseminating or linking these non-economic motivations that land managers have, we find that we lose some of that fragmentation. We get more spatially structured change that is even slower and even less economically rational. And actually, as soon as we allow our agents to make decisions on the basis of things other than economics, or economics and other things, it's very hard to move back from that bottom plot to something as coherent as the top plot. It's hard to squash the behavior back into its box. Secondly, by its nature, models of this kind are non-equilibrium. They're not forced to match supply and demand levels, for example. It's up to the agents to decide what they do in response to the drivers that the model gives them. And this, in some scenario settings, results in very different results to what an economic model would produce. This scenario combination here, the RCP 4.5 SSP3 scenario combination, is a particularly strong example. You can see the bottom plot looks very, very different. There's a huge amount of extensification in European land use. There's a lot of land abandonment, and there's nowhere near enough food for the European population. And that's because we're not assuming that food production always equals demand. We're just allowing the system to develop. And in this case, it develops into this highly dysfunctional state. And that's largely because in this scenario we have these huge decreases shown here in human, financial and manufactured capitals, which not ordinarily support production in the land system, but in this case they're almost entirely absent by the end of the century, and so land managing agents or actors are simply not able to do the farming or forestry that they were doing at the start of the century. We've also tried introducing institutional actors or agents into the model to allow them to try and control these dynamics. In this case, these represent government agents who subsidize land uses in order to try and ensure that supply will equal demand. There are 4 lines on this plot. The green one is the one to look at. It's the total production achieved relative to the baseline. And you can see that as a shortfall develops, the institutions start to introduce subsidies for production, and almost nothing happens until the subsidy value reaches about 150% of the initial value of production. And then we do get increases in production, but they're highly nonlinear and unpredictable. And that's because they're crossing thresholds, trade-offs with other ecosystem services that are being competed against in the land system, and thresholds in the behavior that we're modeling. So agents suddenly start making different decisions when certain values are crossed. The final example I wanted to show was including socio-ecological feedbacks, and this is an example of model coupling that we'll hear more about later, but here we use the crafty model I've been presenting and the range shifter model of species dynamics, species dispersal, evolution, reproduction in space. And we coupled these models to look at pollinator population dynamics in a changing agricultural landscape. And the plot here shows the coupled and uncoupled model results in blue and yellow respectively. And moving back through this plot, we're increasing the importance of pollination for crop yields. So crops are more reliant on pollination on the left-hand side here. And you can see that as we do that, we get this clear divergence between the coupled and uncoupled models, to the extent that total crop supply on the y-axis at the left-hand side is far lower in the coupled model. And that's because the coupled model enters this feedback loop of agriculture intensification, depriving pollinators of habitat, and therefore having lower yields, and therefore intensifying to try and maintain yields. and so the system goes like this. That also, it emerges, has spatial consequences because high-intensity agriculture cannot persist in the same place and works best when surrounded by habitat patches. So we get, in some simulations at least, the emergence of more efficient land use configurations on the basis of these socio-ecological feedbacks. So yeah, I also wanted to suggest that models of this kind may be more, or may be valuable for normative simulations, for looking at states that we want to reach and then finding out how we can get there. So this is an example of a stakeholder developed vision for European land in 2040. It's called the Regional Connected Vision, and it has regional specialization within Europe, but a consistently high range of ecosystem services provided by European landscapes and very well connected Europe, so a lot of trade between regions and so on. And we ran a lot of simulations to try and identify pathways to this vision, and we found that landscapes like this only develop under certain economic and climatic trading conditions, but within those conditions there are clear behavioral pathways to landscapes of this kind. For example, it requires a high level of heterogeneity between land managers so that we don't get large patches of similar production in areas. We need that diversity of ecosystem services across the board. It also benefits from an irrational dedication to land uses so that external drivers don't prompt all land managers to abandon whatever they've been doing for the past several years and take up something new. And we also found that weak social networks were important here, again to maintain this spatial heterogeneity in ecosystem service provision. So I've been very short. I hope that's not too bad. But my conclusions are that we face socio-ecological challenges across scales, from landscape scales to global scales, and they often depend on the same processes that operate at landscape scales. And we need to get those processes into models. We have a good idea of what those processes are in many cases, but we're usually not modeling them. Technically, we can do that. We have the data resources, emerging data resources, to really calibrate those models. We have analysis techniques that are in many cases young but promising, and we have models ready to do this sort of thing. And the initial modeling that I've shown and other initial models that, early stage models that have been published, suggest that when you include those processes, you get qualitatively different results to when you ignore those processes. So if they're important, we do have to model them for decision support. In conclusion, this seems to be a very promising time to take this new approach in addition to what we're already doing. And I think I would simply add that I'm not proposing a sort of cure-all here, that we still need a diversity of approaches to understand how model structure, process representation affects things, and to understand the uncertainty in these models as well.
Thank you, Calum. So we're going to mostly have questions after tea.
Yep.
But maybe while Adam's coming up, we could take one or two. Yeah.
Quick question. I mean, not that I think that this approach really is really useful, and there are obviously the CGEP approaches that are also looking at that kind of scale. But you said that the data is available, and I'm just wondering, some of the information that, for example, Crafty used, like when do farmers decide to give up and do something else? We don't have this information. We don't ask the farmers. We don't, FADN doesn't have it. So I'm a bit worried about that thing.
We don't have it for everybody. We have pretty good general ideas. We ask some people, of course. We ask some farmers. We have evidence from some places. But we know broad process level things. Likely they don't just give up because there's something slightly more profitable to do. They are dedicated to their land use, and they will maintain it even if they make more money or if they're losing money as best they can. And that, at a base level, should be in these models. And then we have some social survey information and so on from different areas that we can generalize with some risk, of course, but it's still an improvement from the blanket assumption of economic rationality.
Okay, we're going to keep if you could keep the questions till after tea, that'd be great. Thank you very much, Calum. So our second speaker in the